Hey, welcome back, viewers. Stay scientific. Keep questioning the world around you. And, don't forget to experiment and test the world around you as well. So, this is a fascinating thought experiment that really delves into the extremes of human adaptation. Let's break down what would likely happen to such a human visiting Earth. First off, the initial superhuman feeling. Gravity is the most immediate and dramatic effect here. A human adapted to heavier gravity would have incredibly dense bones and, honestly, powerfully developed muscles, especially those anti-gravity muscles, just to support their body weight and move around. Upon arriving on Earth with its lower gravity, they'd feel an immense sense of lightness and strength. Jumping would be effortless and much higher. Lifting objects would feel totally trivial, and running would be incredibly fast. They would basically be a superhuman in terms of physical capabilities compared to Earth humans. Alright, let's take a deep breath, because we're diving into the world of oxygen. Imagine having a respiratory and circulatory system so optimized. You could win a gold medal in breathing efficiently at the Olympics, especially in a low oxygen environment. We're talking about supersized lungs and gas exchange skills that would make even a dolphin jealous, maximizing every last molecule of oxygen from thin air. And don't forget the blood. These folks would have more red blood cells than a vampire's dream, and hemoglobin working overtime to deliver oxygen like a 5-star courier service. Plus, their cells would be absolute pros at using oxygen for energy. Think of mitochondria with tiny capes, saving the day with every breath. So, when they land on Earth and take that first breath of our oxygen-rich air, it's like going from dial-up to high-speed internet. Suddenly, everything's supercharged. They might feel like they've just had 3 espressos. Clear-headed, bursting with energy, and ready to run a marathon without breaking a sweat. Out of breath? Not these superhumans. While the rest of us are gasping on the treadmill, they're just getting started. Earth's oxygen is their secret superpower. However, this superhuman state, well, it would be temporary. The human body is amazingly adaptive, but it adapts to the current environment, not against it. So, gravity's toll, bone density loss, is a big one. Without the constant stress of higher gravity, their bones would begin to demineralize and lose density. This is actually a well-documented effect of microgravity on astronauts, leading to osteoporosis-like conditions. Over time, their bones would become weaker and more brittle. Muscle atrophy is another issue. The powerful muscles developed for a high-gravity environment just wouldn't be needed as much anymore. Use it or lose it really applies here. Their muscles would gradually atrophy as the body reallocates resources. While they'd still be stronger than an average Earth human for quite a while, their absolute strength would definitely decline. And then there's cardiovascular deconditioning. Their cardiovascular system, which was adapted to pump blood against stronger gravity, would start to decondition. They might experience things like orthostatic intolerance, which is dizziness upon standing, as their body adjusts to less resistance in blood flow. So, picture this. Their body's supercharged oxygen systems would start to chill out, like a marathon runner who just discovered the joys of binge-watching TV. Their red blood cell count might drop, and their respiratory system could get a little lazier. Think of it as their lungs hitting the snooze button. After all, if there's plenty of oxygen around, why work overtime? Even lungs appreciate a good break. Sure, they'd still be more efficient than your average couch potato or Earth human, But those fancy adaptations, yeah, they'd fade faster than your New Year's resolutions. Now, would their strength remain, allowing them to perform superhuman feats? Well, for a while, yes, they'd be capable of truly superhuman feats compared to Earthlings. The initial period would be one of significant advantage, all thanks to their prior adaptations. But as months and years go by, their body would adapt to Earth's less demanding environment. Their bone density and muscle mass would decrease, eventually bringing their physical capabilities closer to the range of an Earth human. Still, they'd probably be on the stronger end if they kept up a physically active lifestyle. But in the end, they'd lose that superhuman edge as their body adjusted to the new normal. In essence, their body's remarkable ability to adapt would really be a double-edged sword, sharp on both sides, and probably not something you'd want to juggle. It would let them thrive on a high-gravity, low-oxygen planet, basically turning them into the Olympic champions of heavy worlds. But drop them into a less demanding environment, and suddenly, all those superpowers vanish faster than your motivation on a Monday morning. Maintaining the original superhuman form of a human born on a high-gravity, low-oxygen planet would honestly require a highly specialized and technologically advanced routine here on Earth. The main goal, really, is to constantly simulate the environmental stressors that shape their unique physiology in the first place. So, here's a quick breakdown of the routine and technology that would be needed. The routine would focus on high G training and specialized conditioning. This person would need to counteract Earth's lower gravity and higher oxygen levels with an intensive, consistent, and scientifically monitored regimen. High G training sessions would actually happen daily or even multiple times a day. Centrifuge training is, hands down, the most direct way to simulate higher gravity. The individual would spend significant portions of their day in a human centrifuge, which is designed to generate forces far exceeding Earth's 1G. And, these sessions would need to be really carefully calibrated to mimic the specific G-force of their home planet. But it's not enough to just sit in the centrifuge. They need to perform a full range of high-impact, weight-bearing, and resistance exercises while under high Gs. This would include things like heavy compound lifts, squats, deadlifts, presses, and rows, with extremely heavy loads relative to Earth gravity, but normal for their perceived weight. They'd also do plyometrics and jumping, simulating explosive movements against their original gravity, and high-intensity interval training, or HIIT, with short bursts of extreme exertion to help maintain those cardiovascular and muscular adaptations to such high demands. A gravity-weighted vest or suit, while not a perfect substitute for true G-force, could be a game-changer. This specialized, extremely heavy, and well-distributed vest or suit could be worn for extended periods outside the centrifuge. It would provide constant, though linear, resistance to gravity, helping to maintain some bone density and muscle mass over time. Okay, so let's talk about oxygen deprivation training, or controlled hypoxia. The individual would need to spend time in controlled environments with reduced oxygen concentrations, which basically simulates the atmospheric conditions of their home planet. This would stimulate their body to maintain its efficient oxygen uptake and utilization, and Under medical supervision, there would be specific breathing exercises and controlled breath-holding techniques, also known as controlled apnea. These would help train the respiratory muscles and increase their tolerance to lower oxygen levels. Alright, let's talk about specialized nutrition and supplementation, because even superhumans can't live on pizza and energy drinks alone. Sorry, college students, their diet would have to be so precisely tailored, it'd make a Swiss watch jealous. We're talking about fueling muscles and metabolism that work harder than a barista during finals week. That means mountains of protein and enough calcium and vitamin D to make your bones say, "Thank you, kind human." Sorry, cheese lovers. You still need the supplements. And let's not forget the muscle growth supplements, because nobody wants their biceps to go on vacation while the rest of them is working overtime. Plus, scientists are still figuring out how to stop muscles and bones from pulling a disappearing act in microgravity. Just ask any astronaut who's tried to flex after 6 months on the ISS. If we ever get safe, widely available pharmaceuticals that boost bone growth or keep muscles from slacking off, like myostatin inhibitors or hormone therapies, superhumans might finally have an excuse to skip leg day. Maybe. Until then, expect a daily routine that looks like a cross between a science experiment and a vitamin commercial. Superhuman status, sponsored by supplements. And finally, there's constant monitoring and adjustment, real-time biometric tracking of things like bone density, muscle mass, oxygen saturation, cardiovascular markers, and metabolic rates would be absolutely crucial to fine-tune their routine and make sure they're not deconditioning. The exact intensity, duration, and frequency of all these activities would need to be highly individualized and honestly, constantly adjusted based on their physiological responses. So, to make this whole routine possible, we'd need some pretty advanced technology. First up, let's talk about human centrifuges. We're not just talking about the ones astronauts train in right now. These would have to be massive, multi-axis centrifuges, big enough for full-body movement and exercises. They'd also need to generate consistent, precise, and variable g-forces, matching the exact gravity conditions of the original planet. And if that planet had, say, unusual rotation or tidal forces, the multi-axis capabilities could even simulate those complex g-vectors. Plus, the centrifuge would have to seamlessly integrate advanced strength training and cardio equipment that can actually work under those high G loads. And of course, you'd need real-time, non-invasive sensors to track vital signs, muscle activation, bone density changes, maybe even using portable DEXA-like scanners, and all sorts of metabolic markers, right while the centrifuge is spinning. Next up, let's look at controlled hypoxic and hyperbaric environments. We're talking about atmospheric chambers that can precisely regulate oxygen, nitrogen, and other atmospheric gases, plus pressure, to perfectly mimic the alien planet's environment. These could be single rooms, or even entire habitats, and to make sure it's safe and efficient, especially in those closed, low-oxygen environments. You'd need some pretty advanced air filtration and recycling systems. And finally, adaptive exoskeletons and resistance suits, because who needs a gym membership when you can wear your workout? Instead of just strapping on some weights, imagine an advanced exoskeleton that can actively generate resistance against your movements, like having a personal trainer who never gets tired or distracted by their phone. It dynamically simulates what it would feel like to be heavier, just like on your home planet, but without the extra baggage fees. This would be programmable, so you could adjust the resistance based on your movement and the G-force you want to simulate. Finally, a suit that understands your mood swings. And okay, if we're really dreaming big, picture magnetic or even gravitic boot plates. Moonwalking not included. If we ever figure out how to manipulate gravitons, these could pull you down with extra force. Talk about being grounded, so you'd feel heavier without actually adding any physical mass. Pretty wild, right? And hey, your scale will never know the difference. Alright, let's dive into advanced material science for equipment, because regular gym gear would probably just tap out in a high-gravity world. Exercise equipment for these environments. Forget steel. Think superhero-grade alloys. If your dumbbells start flexing, you know you got a problem. We're talking materials so strong, even your ego would have a hard time bending them. These things have to survive more stress than a student during finals week. And hey, if you do manage to break something, besides your personal record, you'll want prosthetics that are light, strong, and maybe even stylish, because nothing says superhuman like a carbon fiber leg that matches your gym shoes. Now, as we turn our gaze to biomedical countermeasures, we find ourselves at the crossroads of science and philosophy, where the age-old quest to transcend our biological limits meets the cutting edge of future pharmaceuticals and gene therapy. Imagine, if you will, targeted drugs, crafted with almost Socratic precision, designed to awaken osteoblasts, the bone-building artisans within us, while simultaneously quieting the osteoclasts, those relentless sculptors who chip away at our bones. All in the name of staving off the slow erosion of demineralization. And yes, perhaps there will be potions. Okay, drugs, to halt muscle atrophy, or even spark new growth, even as we remain tethered to the familiar pull of Earth's gravity. The philosopher's stone for our muscles, perhaps. But let us venture further. With gene therapy and CRISPR, we flirt with the very code of life itself, seeking in theory to etch certain physiological adaptations into our DNA, so that our muscles and bones might become stoic, almost platonic ideals, resistant to the temptations of Earth's lesser gravity. Or perhaps we could even grant ourselves the gift of ever-flowing vitality, permanently boosting red blood cell production, a modern twist on the ancient dream of human enhancement. So, in conclusion, for someone to keep up their superhuman form here on Earth, it would honestly take a constant, tech-driven struggle against natural adaptation. It's like an incredibly demanding and expensive task, basically meaning they'd need to live in a controlled, artificial version of their home planet's environment for a big chunk of their life. But it also raises a deeper question. If we must go to such lengths to maintain superhuman abilities, are we losing touch with what it means to be human? Perhaps the true cost of superhumanity isn't just physical or financial, but a philosophical one. The struggle between transcending our nature and embracing it. You're hitting on a crucial point about the difference between speed and acceleration, or G-forces. So, let's break it down. Speed, or velocity, itself generally has no direct physiological effect on a human body, as long as it's constant. If you're traveling at, say, Mach 10 in a perfectly straight line at a constant altitude, you wouldn't actually feel anything once you've reached that speed. The real challenge with speed in aircraft is the acceleration required to reach that speed, or to change direction at that speed. G-forces, which are all about acceleration, are the forces that push or pull on your body when your velocity changes. And honestly, this is what causes issues for pilots. How would a heavy gravity human fare? Well, you are absolutely correct that a human born and adapted to a planet with heavier gravity would have a significantly higher tolerance for positive g-forces, or plus gz. And here's why. On a high-gravity planet, their heart and blood vessels would have to work constantly against a much stronger gravitational pull to pump blood upwards to the brain and other vital organs. This would result in a more powerful heart, one that's capable of generating much higher blood pressure. They'd also have more robust blood vessels, especially in the lower body, to resist blood pooling. Plus, their baroreflexes, the body's natural mechanisms for regulating blood pressure, would be highly attuned to extreme shifts. When a fighter pilot pulls a high plus G's maneuver on Earth, blood is forced from their head towards their feet, leading to things like grayout, which is loss of peripheral vision, blackout, which is total vision loss, and eventually G-lock, or G-induced loss of consciousness, as the brain is deprived of oxygen. Our high-gravity human system would be inherently much better at resisting this blood pooling. They'd have denser bones and stronger muscles, as we've discussed. So their skeletal and muscular systems would be incredibly robust. This means they'd be far more resistant to the compressive forces that high G's exert on the spine and other bones. Fighter pilots often suffer from chronic back and neck pain due to repeated G loads. But our adapted human would be much less susceptible to such injuries. So, yes, it is highly likely that such a human could, fly the fastest planes with significantly less effect from G-forces. They would experience blackouts and G-lock at much higher G-loads than Earth-born fighter pilots, possibly even pushing beyond the structural limits of current aircraft or the limits of what a typical G-suit can assist with. And, withstanding more extreme maneuvers, they could execute tighter turns, pull up harder, or accelerate and decelerate more rapidly without succumbing to the physiological effects that incapacitate regular pilots. But there are some caveats. Negative G-forces, or minus G's, happen when blood rushes to the head, like during inverted flight or certain dive maneuvers. The human body generally has a lower tolerance for negative G's, since there are fewer natural mechanisms to prevent excessive blood flow to the brain. While their cardiovascular system would be generally stronger, it's not really clear if they would have a drastically improved tolerance for negative G's beyond what an Earth-born pilot might, since this is more about intracranial pressure than blood pooling in the lower extremities, and looking at long-term effects, even with their adaptation, sustained extreme G-forces can still cause wear and tear on the body. While they might be more resilient, they wouldn't be entirely immune to the long-term musculoskeletal or cardiovascular strain if they were constantly pushing the absolute limits of current aircraft. When pondering the limits of aircraft, we quickly discover that the real bottleneck isn't the sky, but the machine itself. Proof that even our wildest dreams are sometimes grounded by nuts, bolts, and the laws of physics. Most fighter jets are built to handle between 9 and 12 Gs, because apparently even the bravest pilots and the most expensive jets have to respect the universe's speed limits. Some experimental aircraft can push those limits, but as any philosopher or test pilot will tell you, pushing boundaries is a great way to find new ones. A human with superhuman G tolerance might survive maneuvers that would turn a regular jet into very expensive confetti. It's a reminder that sometimes The body is willing, but the airframe is weak. Now, about deceleration. Our hypothetical hero could handle sustained Gs, like a Zen master handles distractions, but sudden stops, like in a crash, are the universe's way of reminding us that momentum is a harsh, unforgiving philosopher. Denser bones might help resist fracturing, but even the sturdiest skeleton can't argue with the laws of kinetic energy, no matter how persuasive your bone density is. Because as every philosopher knows, it's not the fall that gets you. It's the sudden stop at the end. Colonel John Stapp's rocket sled experiments proved humans can survive over 40 Gs, at least for the briefest of moments. And with the right paperwork signed. But remember, these feats happened in highly controlled environments with specialized restraints, because even philosophers wear seatbelts when contemplating the limits of acceleration. In the end, whether you're a jet, a human, or a philosopher, it's wise to respect your limits, unless you enjoy learning about them the hard way. In summary, their unique physiology would indeed make them exceptionally well suited for high-G aviation, potentially making them, the ultimate fighter pilot. You've hit upon two very insightful points that get at the heart of biological adaptation. First, this would only work for a person born on a planet with those conditions. Correct? Yes, that's largely correct. The superhuman physical characteristics described, dense bones, powerful muscles, highly efficient oxygen utilization, superior G-force tolerance, are actually a result of developmental adaptation. The body's growth and development from conception through childhood and adolescence happens under these constant, extreme environmental stressors. Bones literally remodel and become denser in response to lifelong high gravity. Muscles develop in a specific way to constantly fight that gravity. Organ systems, like the heart and lungs, grow and mature in a way that's optimized for that particular environment. This isn't just a temporary acclimatization, like an Earth human training at high altitude for a few weeks, but a fundamental shaping of the entire organism's physiology from its earliest stages. Now, when it comes to genetic predisposition over generations, while an individual born in such an environment would develop these traits, for an entire species to truly adapt to these conditions, natural selection over many generations would likely play a role. Individuals with genetic variations that better allowed them to thrive in high gravity and low oxygen would be more likely to survive and reproduce, gradually baking in some of these adaptations into the species' genome. So, a hypothetical human from such a planet would likely have both developmental adaptations and subtle genetic differences from Earth humans. An Earth-born human, no matter how intensely they train, could never achieve the same level of bone density or muscle morphology that develops naturally under constant high-G stress from birth. Their bodies would always be fighting against their fundamental developmental programming. So, what if we use CRISPR-Cas9 to create a human and, actually create the environment they're conceived in? Would that still work? Well, my hypothesis is it would. Your hypothesis is highly plausible, and honestly represents a fascinating frontier. Here's why. CRISPR-Cas9, along with other gene editing technologies, offers the theoretical ability to directly modify the human genome. You could potentially introduce or enhance genes known to be involved in bone density, like those related to osteoblast activity or collagen production, muscle growth and efficiency, such as myostatin regulation or mitochondrial efficiency, and even red blood cell production and hemoglobin oxygen binding affinity. The goal here wouldn't necessarily be to create entirely new genes, but to optimize existing human genes for these extreme conditions, much in the same way natural selection has optimized Tibetans for high altitude, with specific mutations in the HIF pathway, for example. And, crucially, if these edits are made in the embryo through germline editing, they'd be present in every cell of the developing individual and would be heritable. This would pretty much mimic the genetic aspect of natural adaptation. Simulating the environment from conception. This is the second critical piece. If the genetically modified embryo were then conceived, gestated, and developed, say, through an artificial womb or ectogenesis, or even in a highly controlled maternal environment, within a chamber that precisely replicated the high gravity and low oxygen conditions of the alien planet, you'd be combining genetic predisposition with developmental adaptation. The constant physical stress of high gravity during bone and muscle development would trigger the epigenetic responses and physiological growth patterns needed to express the full potential of those gene edits. And the low oxygen environment would, in the same way, shape their respiratory and circulatory systems right from the ground up. But as we simulate entire worlds from the very beginning of life, deeper questions emerge. What does it mean to be human if our reality is engineered from conception? Does identity arise from our genes, our environment, or the interplay between the two? If experience itself is shaped by artificial conditions, can we truly say, what is real? Or are we creating new forms of existence, new ways of being, that challenge the very nature of human experience? These are not just scientific questions, but philosophical ones, inviting us to reflect on the boundaries of reality and the essence of who we are. So, why would it work? At least in theory. By combining sophisticated gene editing to predispose the individual to these traits with a meticulously controlled developmental environment that forces those traits to fully express, you'd basically be replicating the evolutionary and developmental processes that would create such an adapted human naturally. So, let's talk about some of the real challenges and ethical considerations here. First off, the complexity of gene regulation is huge. We're still learning just how genes interact with each other and how things like our environment can influence gene expression. This is what we call epigenetics. It's definitely not as simple as just flipping a single super strength switch. In reality, many genes would have to work together all at once. Then, there's the risk of unintended consequences. Changing fundamental aspects of human biology could lead to side effects we can't even predict yet. And honestly, just creating a stable, long-term environment with high gravity and low oxygen for gestation and development, well, that's a massive engineering challenge on its own. But maybe the biggest question is ethical. This kind of work brings up some really deep questions about designer babies, human experimentation, and even what it really means to be human. Like, who gets to decide what kind of adaptations are desirable? And what rights would an individual like this actually have? From a philosophical perspective, these questions force us to confront the very nature of identity and agency. If we can design or alter humans for specific environments, are we enhancing humanity or redefining it? At what point does the pursuit of progress challenge the essence of what it means to be human? And, perhaps most importantly, do we risk losing something fundamental about ourselves in the process? Still, even with all these challenges, your hypothesis is actually pretty well aligned with what we know right now about genetics, developmental biology, and just how amazingly adaptable the human body can be when faced with consistent environmental pressures. If genetic engineering and environmental simulation ever do get to that point, it's totally possible that we could see humans with adaptations that are, well, superhuman compared to what we know on Earth. The weight of two worlds. The thought experiment of a human born. Under such extreme conditions, whether naturally or by design, culminates in a profound philosophical reflection. What is the true nature of human potential when pushed beyond Earth's familiar confines? This superhuman isn't merely an individual of enhanced physical prowess, but a living testament to adaptation's relentless power, a being whose very physiology embodies the harsh embrace of an alien environment. Their existence challenges our perception of normalcy. What we consider peak human performance, strength, endurance, resilience, becomes a baseline for them, defined by a universe far more demanding than our own. When they step onto Earth, they don't just feel lighter, they experience a fundamental shift in their relationship with the physical world, a constant, effortless overcoming of what binds us. This brief, exhilarating period of superhumanity isn't a magical gift, but a stark demonstration of relativity. Their strength is only super in comparison to our baseline, a baseline shaped by different forces. Yet, as we've explored, Earth's less demanding environment would inevitably begin to resculpt them. Their body, always striving for equilibrium, would shed the very adaptations that made them unique. This inevitable deconditioning highlights a poignant truth. Our biology is not a static blueprint, but a dynamic dialogue with our surroundings. We are constantly becoming, molded by the pressures and opportunities of our world. The superhuman form, whether inherited or engineered, would become a burden to maintain, a constant struggle against the natural tendency towards the path of least resistance. Ultimately, this figure serves as a powerful metaphor for humanity's own journey. Are we defined by our origins, or by our capacity to transcend them? In their existence, we see both the thrilling promise of human augmentation, the ability to deliberately craft beings suited for new frontiers, and the inherent tragedy of dislocated existence. Would such a being ever truly belong? Would the constant battle to preserve their original form be a triumph of will, or a Sisyphean burden? Their very being forces us to ponder. What extraordinary qualities might lie dormant within us, waiting for the right, or perhaps the most challenging conditions to awaken? So, if this idea has sparked your curiosity, don't just let it end here. Dive deeper, ask questions, and share your thoughts with us. Let's keep exploring what it really means to be human.